Hello and welcome back to the channel. Today we are continuing with computational methods subject, and in this video we will look at root finding methods. The contents that we will be covering into this video is bisection method, Newton's method and secant method, and we'll look at their convergence analysis and implementation one by one. Introduction to root finding. So, a root finding algorithm is used to determine the values of x for which fx equals 0. These methods are essential in numerical computations because many real-world problems, including in physics, engineering, and finance, require solving equations that cannot be solved algebraically. So, why we should use root finding methods? So many equations don't have a closed form solution. Some methods provide better accuracy and convergence speed than others. And lastly, it is useful in optimization and machine learning where derivatives play a key role. Like for this, when an equation don't have a closed form solution, we can take an example of x equals e to the power minus x. So we need some another root finding method instead of algebra to find its solutions. The first one is bisection method. So the concept of bisection method is, the bisection method is simple bracketing technique that iteratively reduces the interval containing the root. So it is based on intermediate value theorem, which states that if a function fx is continuous on AB, fa cross fb or multiplied by fb is less than 0, then there exists at least one root c in AB. This is the statement of intermediate value theorem. So algorithm steps in bisection method involves, let's start with algorithm. Step number 1, choose the initial interval AB such that FA into FB is less than 0. Step number 2 is to compute the midpoint, that is c is equals to a plus b by 2. Then there is step 3 for the algorithm to evaluate fc. Now there are 3 conditions to it. If fc equals 0, then c is the root. Second, if fa cross fc is less than 0, then we need to update b equals c, root is in the left half then. Else, we need to update a equals c, root is in the right half. If b equals c, root is in the left half. If a equals c, then root is in the right half respectively. Step number 4 is just that, repeat the steps until desired accuracy is reached in any equation. Moving on to convergence analysis. So the error reduces exponentially with each iteration. That means modulus of En equals modulus of b minus a divided by 2 to the power n, where n is the number of iterations we are doing. So bisection method is guaranteed to converge but can be slow compared to the other method. So implementation considerations when we talk about it involves that it works only if initial interval contains a root. That is, our initial interval was a and b. If this interval contains a root, then only bisection method will work. And it doesn't work well if function has multiple roots within an interval. That means this complete interval only should have c as the root. No d, e and f should be there, else the bisection method won't work in this case. Moving on to the Newton's method or Newton-Raphson method. Newton's method uses tangent lines to iteratively approximate the root. It has quadratic convergence, making it faster than the bisection method. Moving on to its formula, it says xn plus 1 equals xn minus fxn divided by f dash xn, where xn is our current estimate, f dash x is the derivative of the function fx. So algorithm steps involve: step number 1, we need to choose the initial guess, and our initial guess is denoted as x0. Then step number 2, we need to compute the next estimate, that is xn plus 1 equals xn minus fxn and f dash xn. We need to repeat until the convergence criterion is there. That is our step number 3, to repeat until our convergence criterion is met, and the criterion is xn plus 1 minus xn less than epsilon is met. This statement is our convergence criterion. Now let's talk about the convergence analysis. Quadratic convergence, if we talk about, the error reduces superlinearly. That is, it is nearly equals to O(n) square. And if x0 is close to the root, like let's say our root is with c and x0 is close to it, then the convergence is fast. And if x0 is far from the root, far from c, let's say, it may diverge or oscillate. Now, when it comes to implementation considerations, it requires differentiability of fx, and it can fail if f dash x is 0 or very small, causing the division errors. Moving on to the last, second method. The second method is similar to the Newton's method but does not require derivatives. Instead, it approximates f dash x using a finite difference. So the formula for second method is xn plus 1 equals xn minus fxn multiplied by xn minus 1 fxn minus fxn minus 1. This is the formula where xn and xn minus 1 are the two most recent estimates. Algorithm steps include: step number 1 is choose the two initial estimates, that is x0 and x1. We need to choose them. Then step number 2 is to compute the next estimate using the formula. Step number 2, formula. Step number 3 is repeat until the desired accuracy is obtained. When it comes to convergence analysis, so firstly it has superlinear convergence. That is, it is faster than bisection but slower than the Newton's method. And it doesn't require derivatives, making it more flexible. Talking about implementation consideration, it can fail if denominator is too small, that is dividing by near 0, as we had in Newton's method, And lastly, it requires 2 initial guesses instead of 1. Moving on to the quick comparison of root finding methods: bisection, Newton's method, and second method. The order of convergence in each of them is linear, quadratic, and superlinear. No derivative is required in bisection, and second, only Newton's method required a derivative. Stability is that bisection method will always converges, but it is slow. Newton's method may diverge, but it is fast, and second method can fail, but it has medium speed. So in conclusion of this part 2 video on computational methods is that bisection is simple and reliable but slow. Newton's method is very fast but needs a derivative and can fail if the initial guess is poor. Lastly, second method is a practical alternative when derivatives are unavailable to us. So these methods are widely used in scientific computing, engineering simulations, and numerical modeling. So that's all for this video. In the next video, we will look at optimization methods. And if you found this video helpful, give it a like, share it with your friends, and do subscribe the channel to help us grow. And I will see you in the next video. Till then, happy learning.